final frontier. These are the voyages of the starship Enterprise. Its 5-year mission, to explore strange new worlds, to seek out new life and new civilizations, to boldly go where no man has gone before.
Prepare to be mind-boggled! It's funny because on the last video we talked about how mass and energy can be the same thing. We did the whole that math thing, and by then most people are mind-boggled. But now we will go where your mind has never gone before, and I hope you can follow along. Mankind understanding of modern physics has come a long way since science was born again in the Middle Ages. And I say born again because man has always been curious about the way things work. But it's been a challenge during the Middle Ages because of the oppression of one single group controlling what's right and what's wrong. It was kind of hard to diversify and think and be creative. Like Einstein said, imagination is more important than knowledge sometimes. And the limits of imagination are going to be pushed right now in this video, and I hope you guys can follow along with what I'm trying to say. I just wanted to cover the main strands of physics over the last few centuries. And let's all start it perhaps with the father of physics, the father of modern physics, which would be Isaac Newton. And basically he did so much. You gotta give it up to this guy because he was amazing. He talked about that law of action and reaction. You know, everything you do, something opposite will happen in return. So when you punch the wall punches you. If you're standing on a cart while you do that, the car will go the opposite way. When you go the other way, you will fall. You hit the floor, the floor hits you, you get hurt, and so forth. All of these things. He also talked about inertia. An object will not change its acceleration pattern unless a force is acted upon it. In other words, if it's going fast, it's going to stay fast. If it's going slow, it's going to stay slow. If it's stopped, it's going to stay stopped unless a force acts upon it. And that's what makes you move forward. And when the car stops, during a car crash, because it's the car that's stopping, not you. And it's what makes, for example, when you flick a paper and a coin is staying on top of it on a cup, you flick the paper go, but the coin does not because the coin was not acted on, only the paper. But then a force starts acting upon the coin and it falls because gravity acts on it. All of these are great examples of inertia. And inertia also explains why objects of different mass fall at the same rate. You get a lighter object and an object that's heavier, like the cap and the pen. The pen will fall at the same time that the cap will, because even though gravity is acting on both objects and gravity is going to be stronger among the heavier object and the earth, the inertia is also going to be larger for the object that's more massive, and it's going to be harder for the motion to actually begin because of inertia. Remember, inertia is not a force. It's more like a property of matter, which things have to beat in order to actually move. He also talked about that the amount of force that's applied to an object is directly proportional to the mass in order to determine the acceleration. In other words, an object that is very massive, if the same force is applied to the object as an object that's very light, the object that's massive will move less than the object that's light because it takes more power to move a heavier object. It goes back to the idea of the inertia that must be broken. He also studied orbits and how orbits work. He actually explained Kepler's laws. Remember, Kepler talked about the law of periods, the law of ellipsis, and the law of equal areas to explain the ways that planets orbit around each other. But it was Isaac Newton that explained why the planets were orbiting, because of a balance between inertia, or the centrifugal force of the object that's spinning, being thrown out of the orbit, and gravity that's pulling it in, keeping the object in balance. He was the first one to talk about position, time, energy, acceleration, velocity, and all these things we talked about at the beginning of the year when we did space. And here we are again, talking about him. Very important. And the next big advancement in physics came with Albert Einstein. And what Albert Einstein did is that he threw everything that Newton said in the trash. You know, for example, things don't fall, for starters. They actually roll down a gravity hill. Einstein's general relativity theory explains that gravity is actually bending the space-time continuum, and the mass of the objects actually bends the space and the time around it. In other words, time passes down slower for people who are closer to the ellipsis created by the gravitational force that bends the space-time. So someone on top of Mount Everest will age faster than someone who's actually close to the center of the Earth. He also talked about special relativity, or the idea that objects moving faster, time goes by slower for those objects. So that the faster you move, the slower time goes by. And that must be true since the speed of light is constant everywhere you look in the universe. We talked about this when we did space in the beginning of the year. He also was the first one to explain the idea of gravity and orbits with completely new equations that took in consideration that space is actually curved, which helps us understand why gravity causes objects to bend around. For example, even light bends around massive stars, and it causes what is called the gravitational lensing effect. Remember we talked about that? He also talked about the fact of the duality of energy and matter, that matter and energy are all the same thing. He came up with ideas such as gravitational singularities of black holes. All of these things came from Einstein's relativity theory. Everything is relative. You know, there's no up, there's no down, there's no fast, there's no slow, there's no time, there's no space. It's all one thing, it's all nothing. It's all about Einstein. Crazy guy, sitting in class thinking about these random things and actually creating a whole new way of us understanding the universe, which is actually proven by data. And it's the same kind of formulas that we use to send people to the moon. But Einstein was not completely right. You see, his relativity theory is really good when it talks about macro things or the way the big things work. But when you start looking at microscopically, the way that things work at the microscopic scale, relativity doesn't really talk about that. And so came another group of scientists that did something that's called quantum physics. Now, quantum physics is the study of small stuff. And we're going to talk about that in the next video when we do the particles of matter. Everything we're going to talk about is basically the discoveries that have been made through quantum physics. But quantum physics has ideas like, you know, for example, two things can't be in the same place at the same time. Says who? Particles are so small and so fast sometimes that they're everywhere and nowhere at the same time. We talked about that in the beginning of the year. Remember, we talked about the idea that electrons move around the nucleus so fast that they're everywhere in the atom and nowhere at the same time. You will never be able to catch one. But if you try to ask the atom, where is this electron right now? It's probably right there. But if you try to catch it, it's already somewhere else. So it's everywhere and nowhere at the same time. In one split second, it will be everywhere in its orbit. But it will be nowhere in its orbit if you actually try to catch it. And remember, the actual act of trying to see it will put light on it, which will give electricity to it, which will make it move. So when you try to observe a phenomenon, you actually change the phenomenon. For example, if I get a bird and I put it inside my hand and I squish it, now, is that blood dead or is it the blood alive? Well, until I open my hand and see what happened, both things are true. It's possible that both things happen, and that's called the Schrodinger's paradox. We'll talk about that when we do the review of the history of science later in the lecture series. But it's all about the uncertainty of the observation of things which are so small that you can't even know if they exist. Then is the idea that multiple realities can exist at the same time, or that every decision that you make happened somewhere else. And so that right now you're deciding to watch this video in another universe, you didn't even watch it and you failed the test. So quantum physics is really about trying to understand that when you study small things, you start noticing different patterns of reality. For example, that energy is not continuous, that you get to a point where you can't add just a little bit more. You have to add them in small packets that we call photons, right? And that comes from Einstein's particle duality thing, where particles can act both as waves and as particles, depending on how you look at it. So is it one or is it the other? Well, it's both until you actually look at it, some quantum physics would say, or both are happening in multiple realities. And every time we actually make a measurement or make a decision, a different reality presents itself. But in another universe, the opposite reality actually took place. And all of these things coexist all in the same place. And that's what makes it crazy. And at the same time, the quantum physics says it's impossible for two particles to be in the same place. Only, of course, if they are opposite to each other in the sense of the way they are in reality, or the way they spin. So if you actually have two electrons, they cannot occupy the same space, even though the electron is everywhere and nowhere in the atom at the same time. It's impossible to determine both the position and the momentum, in other words, how it's moving the particle at the same time. This world of small things is not like the world of big things we live in. Things do crazy things in the world of small things. And infinity becomes just as important as smallness. The smallness just shows you how there's infinite number of experiences or opportunities that can actually take place, and that all of them coexist until finally you start studying them. And there's a lot more that I could say about quantum physics, and this is just kind of like giving you a taste for it. And so quantum physics, it's an advancement of the study or understanding of the universe that has to do with the uncertainty of studying something. The uncertainty of studying things which are so small, and yet the certainty that they're there all at the same time. So the idea of superposition, that it's possible to be 1 and 2 or nothing all at the same time. But then people are boggled by the fact that quantum physics says something for small things and relativity says something else for large things. And people sought to find a way to conciliate quantum physics and relativity. And they came up with the idea of string theory. And this was becoming popular starting with the late 70s and into the 80s. And it's basically the idea that everything there is in the universe is basically manifested by strings of space-time. Just like, in quantum physics they say there's multiple realities that coexist all at the same time. In string theory, we explain each of these realities as a unidimensional string of space-time. And that what you experience as gravity, as mass, as energy, as electromagnetism, is just one of these strings which is interlaced with another string. So for example, magnetism is basically created by two superimposed strings. One that's acting on mass, one that's acting on charge. So the different things you experience of the universe are different strings of space and time. But these strings can coexist with multiple other strings. And Einstein described in relativity space-time as a four-dimensional structure. You have width, length, and height, and then time. So you have to experience space-time in 4 dimensions. So it's not where you are only, but where and when you are. And then string theory gets that aspect of relativity and talks about, in fact, that there's not just 4 dimensions, but 10 dimensions. And the extra dimensions are things like gravity and electricity and magnetism, different strings of space and time, which we only experience when one of these strings vibrates and interacts with our own 4 strings of space and time. This is a lot of complex stuff, but the way I try to think of it is that everything there is a convoluted mess of strings which gets together to make a texture. It's just like your shirt is put together of many tiny little fibers. And what you experience as the connection between the fibers, or gravity, is actually created at the fiber level as one fiber connects to the other. So I think of string theory as multiple strings of space-time vibrating next to each other like this. And every time one string touches another, a different aspect of reality is created. And the Big Bang is basically an event that happened because the strings hit each other. And so that's kind of what string theory is talking about. But the problem is that for the formulas that were created because of string theory, just like relativity created new formulas, and quantum physics created new formulas, mathematical formulas created by string theory can be interpreted in multiple different ways. And since the 80s, 5 different branches of string theory have evolved by interpreting the equations in 5 different ways. And people have been trying very hard to reconciliate these 5 different types of string theory. And so where we are right now, since the 90s, is the idea of M theory, which is that instead of thinking of unidimensional strings, which are all vibrating next to each other and hitting each other, creating the different aspects of reality, those multiple strings of space and time connect together somehow as they hit each other, and they form a texture which we call the matrix of what is. And I think of that as unidimensional strings forming 10 dimensions within a 2-dimensional texture, which then folds in 3 dimensions. So it's 10 dimensions within 3 dimensions. I have no idea what they're talking about, but it helps people understand the way the universe works and why it does what it does. And I don't expect you to understand this. It's just to show you what's out there. And the search is really for the theory of everything, like Stephen Hawking would say, or the idea that would actually explain everything there is and everything that happens since the beginning until the end. Everything in physics. M theory is the closest we've gotten to it, but it's not quite completely able to understand how the universe works and why things like gravity and space and time and everything else there is exist. What are these strings of existence that we're talking about? In the next video, we're going to talk about particles of matter. I'll see you guys then.